Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
What shape is an asteroid?
Yeah, it sounds like a question a kid might ask you, right?
Exactly. It's a seemingly simple, innocent question. But if you actually stop and think about it, if you consider the history of how we've looked up at the night sky, for the vast, vast majority of human history, the honest answer has just been, nobody knows.
Right. Because for centuries, they've literally just been dots.
Just tiny, featureless points of light. Right. Crawling against the backdrop of the stars. I mean, if you look at the etymology, the word asteroid actually means star-like.
Which makes total sense, because when you look at them through a traditional telescope, that is exactly what they appear to be. They don't resolve into planetary disks.
Right. No visible weather systems or rings or anything.
Exactly. Due to the diffraction limits of early optics and honestly just the sheer distance involved, they're just specks. They're just mathematical coordinates in the dark.
Which has to be incredibly annoying for planetary scientists.
Oh, it's more than a minor annoyance. It's been a fundamental roadblock in understanding our own cosmic neighborhood. Because when you can only observe a dot of light, you're forced to categorize the entire solar system based just on how that tiny point flickers.
So you're working with this massive data deficit right from the start.
You really are. I mean, you know something is out there, and you can track its orbit, sure, and you can maybe use spectroscopy to guess what the surface is made of. But the actual physical geography of the object, that remains entirely hidden.
Well, today, you and I are embarking on a mission to unravel the mystery of one specific, highly unusual space rock that has pushed the absolute boundaries of our observational tech. It's known as Asteroid 44 Nysa.
Oh, Nysa. That is a name that commands a profound amount of respect and, frankly, frustration in astronomy circles. It's a world that has teased us for generations.
Okay, let's unpack this, because this isn't just a casual conversation about a weirdly shaped rock tumbling through the void between Mars and Jupiter. This is about fundamentally understanding the building blocks of our own solar system.
Absolutely. It's about looking at a piece of cosmic debris and trying to read the physical history of the universe written right there on its surface.
Right, because Nysa isn't just a rock, it is a time capsule. It's a physical remnant from that chaotic, violent era when the planets, including the Earth we're sitting on right now, were actively being forged out of dust and gas.
The stakes are incredibly high with primordial bodies like this. Every time we manage to resolve the actual shape of a new asteroid, we aren't just getting a cool desktop wallpaper. We are rigorously testing our overarching theories of planetary formation.
Like, how does a microscopic grain of dust become a pebble?
Exactly. And how does an aggregate of pebbles become a boulder? And by what actual mechanical process do those boulders stick together to build a whole world?
So to understand why Nysa is so special and why it holds the key to those massive questions, we first have to understand why astronomers have been staring at it in utter frustration for well over a century. Let's start with the name.
Right. Asteroid 44 Nysa.
That number, 44, it isn't just random, right? It's historical. It signifies the order of discovery. So Ceres is 1, Pallas is 2, and so on.
Which means being number 44 puts Nysa very early in the timeline of modern astronomy.
Right. It was discovered way back in 1857 by Hermann Goldschmidt. So for nearly 170 years, we have known the specific rock was out there.
Yes, orbiting in the main asteroid belt between Mars and Jupiter. And it's one of the brightest objects in that entire sparse ring of debris.
Why is it so bright, though?
That brightness is the crucial factor. Nysa belongs to a very specific, somewhat rare class of asteroids. It is an E-type asteroid, and it happens to be one of the largest E-types out there.
The E stands for enstatite, right?
Spot on. Enstatite is a specific type of silicate mineral, a magnesium silicate. And what makes enstatite surfaces so fascinating is that they are incredibly reflective. They have a very high albedo.
Because most asteroids are pretty dark, aren't they?
Yeah, the vast majority are C-type, which are carbonaceous. They absorb most of the light that hits them. Think of, like, the color and texture of a charcoal briquette.
Oh, wow, that dark.
Very dark. Or you have S-types, which are stony and only moderately reflective. But E-types, like Nysa, they are brilliant. They reflect a massive percentage of the sunlight that hits them.
So it's basically acting like a giant tumbling mirror out in deep space.
Pretty much. Which perfectly explains why Goldschmidt was able to spot it so early in 1857. Even though Nysa is relatively small on a planetary scale, it's acting like a cosmic beacon.
But here's the crux of the frustration for you guys. Because it is so unusually bright, and because it has this bizarre and stay-tight composition, it has been a favorite high-priority target for over 100 years.
Oh, completely. Generation after generation of astronomers have pointed their best instruments at it, trying to figure out what it physically looks like.
And for a century, the data coming back has just been maddeningly ambiguous.
It really has. Because before modern high-resolution imaging, astronomers were forced to rely on a technique called photometry to generate light curves.
Which is an elegant concept, but super indirect, right?
Very indirect.
Yeah.
As an asteroid rotates on its axis, the amount of sunlight it reflects toward Earth changes depending on its shape.
So if you have a perfectly spherical asteroid, the surface area facing us stays constant as it spins.
Exactly. Therefore, its light curve, which is just a graph of its brightness over time, is a relatively flat, straight line.
But if you have an elongated asteroid or something irregular, the physics of that reflection changes entirely.
Right. When the broadside of a tumbling, elongated rock faces Earth, it reflects a ton of light and the curve spikes.
And then as it continues to rotate and the narrow end points toward us, less light is reflected and the curve dips.
You got it. So by measuring those peaks and valleys in brightness over hours and days, astronomers use complex mathematical inversion models to try and reverse engineer a 3D shape from a 2D line graph.
But that math is tricky, isn't it?
It's notoriously non-unique. You can have entirely different physical shapes that produce the exact same flickering pattern of light.
So you're just guessing, basically.
For decades, the light curves of Nysa were just screaming at astronomers, "I am not a sphere!" The amplitudes of the brightness variations were way too extreme for that.
So successive observations hinted it was elongated, maybe even bifurcated, like two distinct lumps stuck together.
But that picture remained just a hypothesis. It was a shadow on a graph, a statistical probability, not a physical place you could actually verify.
I like to think of this historical predicament like trying to read a blurry license plate through a cheap pair of binoculars from miles away on a really hot, shimmering day.
That is a very accurate analogy.
Right. You know a car is there. You can see the shape changing slightly as it turns. You can see the sunlight glinting off the metal, but you just can't bring it into focus.
The optical resolution simply isn't there. You're left guessing based on blurry smudges. And the intellectual itch that creates for a scientist is profound.
I can imagine. You dedicate your career to studying this object, and it's just out of reach.
You know a secret is hidden just out of focus. You know it's weird, you know it's not a normal rock, but you cannot empirically prove your models.
Well, that exact intellectual itch is what drives the most massive leaps in technological innovation. Astronomers didn't just throw up their hands, they waited for the engineering to catch up.
And that brings us to the technological leap that finally pierced through that century of blurry frustration.
And what I love is that this leap didn't come from launching a multi-billion-dollar robotic probe to fly past Nysa.
No, it didn't. It came from two of the heaviest, most advanced, most mind-bogglingly complex instruments ever constructed on Earth, firmly planted on the ground.
We are talking about an international team led by Kate Minker at Lowell Observatory. They decided to tackle this enigma using some absolute titans of modern astronomy.
They utilized the Shark-Viz instrument mounted on the Large Binocular Telescope in Arizona, and they combined that with data from this Spheres Impel instrument on the Very Large Telescope in Chile.
Okay, to appreciate the magnitude of what Minker's team accomplished here, we have to talk about the physical enemy they were fighting. Why is looking at space from the Earth so difficult?
The fundamental antagonist to ground-based astronomy is our own atmosphere.
I mean, we obviously need it to breathe.
Sure, for survival it's great. But for an astronomer trying to resolve a 75-kilometer rock hundreds of millions of miles away, the atmosphere is essentially a distorting funhouse mirror.
Because it's never static, right?
Never. It is a chaotic, turbulent, churning ocean of gas. You have pockets of hot air rising, cold air sinking, extreme wind shear, variations in humidity.
And all of that messes with the light.
Exactly. In optics, we measure how easily light travels through a medium using an index of refraction. When air changes temperature or density, the refractive index changes.
So imagine the journey of the light. The sunlight hits Nysa, bounces off, and begins a pristine journey across millions of miles of the absolute vacuum of space.
And in a vacuum, there's nothing to distort it. The wave front of that light is entirely flat and uniform.
Until the very last fraction of a second.
Right. When that perfectly flat wavefront hits the top of Earth's atmosphere, it enters that turbulent ocean. It passes through thousands of moving pockets of air,
Each acting like a weird, weak little lens.
bending and warping the light in random directions. So by the time that light hits the telescope on the ground, the flat wavefront looks like a crumpled up piece of paper.
This atmospheric distortion is exactly what causes stars to twinkle when you look up at night, isn't it?
Yes. The poet looks at a twinkling star and sees romance. The astronomer looks at a twinkling star and sees a catastrophically degraded data point.
That is hilarious, but true. You guys call it astronomical seeing, right?
We do. If the atmosphere is particularly turbulent, the seeing is bad, and the point of light is smeared out into a fuzzy, boiling blob on the sensor.
Traditionally, the only way to defeat this was just to bypass the atmosphere entirely. Put a telescope on a rocket and put it in orbit.
Which was the entire driving philosophy behind the Hubble Space Telescope. Hubble isn't actually that large. Its mirror is only 2.4 meters across.
But it's in a vacuum.
Exactly. It can achieve its maximum theoretical resolution without any atmospheric smearing.
But Minker's team studying Nysa didn't use Hubble or James Webb. They used ground-based telescopes equipped with adaptive optics.
Which is arguably one of the most brilliant optomechanical engineering feats of the last 50 years.
It sounds like science fiction. How do you physically correct a chaotic, unpredictable atmosphere in real time?
The concept is to measure the exact distortion caused by the atmosphere instantly, and then physically change the shape of the telescope's mirror to introduce the exact opposite distortion.
Wait, you're bending a solid glass mirror. Are they bending the giant primary mirror at the bottom of the telescope?
No. Those primary mirrors are massive. The Very Large Telescope uses mirrors that are 8.2 meters across and weigh tons. They're totally rigid.
So where does the bending happen?
The adaptive optics system happens further down the optical path. The light bounces off the giant primary mirror up to a secondary mirror and into an instrument suite that contains a specially designed deformable mirror.
A deformable mirror. What is that actually made of?
It's an incredibly thin, flexible membrane of reflective material, sometimes just a few millimeters thick, and mounted directly behind it are thousands of microscopic actuators.
Like tiny pistons.
Exactly. Often voice coils or piezoelectric crystals that expand and contract when you apply voltage to them. They push and pull on the back of the flexible mirror.
But the atmosphere changes millisecond to millisecond. How does the computer know exactly how to bend the mirror that fast?
You need a reference point, something whose original shape you already know perfectly. Often, they will shoot a powerful, precisely tuned laser straight up into the night sky.
Wait, a laser?
Yes, tuned to excite a layer of sodium atoms sitting about 90 kilometers up in the mesosphere. It's leftover dust from micrometeors burning up.
So the laser hits the sodium and makes it glow.
Right, creating an artificial guide star right next to the object you actually want to look at.
That is wild. You are creating a fake glowing star high in the atmosphere just to measure the blur.
Because you created it, you know the light originating from it should be a perfect, sharp point. A sensor in the telescope look at how much that artificial star has been smeared by the trip back down.
I see the loop now. The sensor calculates the mathematical inverse of this smear, sends a signal to the tiny pistons, and they push the mirror into a shape that perfectly counteracts the distortion.
And the staggering part is the speed. It measures the distortion and physically bends the mirror hundreds, sometimes thousands of times every single second.
It's flattening out a churning ocean of air in real time.
It really is.
By doing this, Minker's team achieved something historic. They produced the highest resolution images of Nysa ever obtained. They described them as being close to spacecraft quality without ever leaving Earth.
It's an astonishing achievement for ground-based astronomy.
Now, wait a minute. Let me push back on this for a second. If we are getting spacecraft quality images from ground-based telescopes, how does that work practically? Does this technology make sending robotic space probes redundant?
This raises an important question, and it is a debate that echoes through funding agencies constantly. But the short answer is, absolutely not. Space probes are not remotely redundant.
Okay, why not? If we can just build better mirrors on Earth, why spend billions launching a fragile metal box into the void?
Because the roles they play are totally different. Ground-based telescopes can be built unimaginably large. We're building the extremely large telescope right now, which will have a primary mirror nearly 39 meters across.
You definitely cannot fold up a 39-meter mirror and pack it into a rocket.
Exactly. The raw light gathering power on the ground will always scale faster and cheaper. Plus, if it breaks, a technician can just drive up the mountain and swap a circuit board.
If a probe breaks, it's just gone.
Right. So for spotting faint objects or high-res visual maps of things we know exist, ground-based adaptive optics is the vanguard. But visual observation is just one narrow slice of the pie.
Right, an image is just photons hitting a sensor.
A telescope on Earth cannot fly through the coma of a comet and physically sample the dust. It can't use a mass spectrometer to smell the chemical outgassing. It can't drop a lander to drill into the surface.
So the telescope provides the high-resolution map, but the spacecraft is required to actually walk the territory.
That is the perfect way to contextualize it. They are highly complementary. We use the ground to survey thousands of objects and find the weirdest anomalies like Nysa.
And then you know exactly where to send the probe later to get the best return on investment.
Exactly.
Okay, so let's return to the specific anomaly in question. Minker's team points these colossal machines at Nysa. The lasers pierce the mesosphere, the mirrors vibrate thousands of times a second, the image finally resolves.
And it completely defies a century of careful modeling.
What did they actually see?
Well, the light curves had suggested an elongated potato shape, maybe 2 lumps. But the adaptive optics images didn't just show a lopsided rock. They clearly revealed 2 incredibly prominent, deep valleys wrapping completely around the asteroid's circumference.
We aren't talking about shallow depressions here, right?
No, these are deep grooves, physical demarcations circling the entire massive rock.
Like it's pinched.
Yes. The team didn't interpret them as random craters or fault lines. The morphology was too specific. They interpreted these valleys as necks pinched joints, where entirely separate physical bodies have come to rest against one another.
Suggesting that Nysa is not a single rock.
Right. The visual evidence strongly suggests it is composed of 3 distinct bulbous lobes, gently welded together into one structure.
3 distinct lobes. That is astonishing.
It's breathtaking. Now, the concept of distinct bodies sticking together isn't totally new. We call it a contact binary.
Let's clearly define that, because when the average person hears binary system, they usually think of 2 stars orbiting each other at a distance.
Right. A standard binary is locked in a gravitational dance, separated by space. But a contact binary means the 2 bodies have actually physically touched and remained together.
How does that even happen? We're so conditioned by Earth's gravity. If I smash 2 rocks together on Earth, they shatter.
Because on Earth, things accelerate quickly and hit with immense kinetic energy. But in the main asteroid belt, relative velocities can be astonishingly low.
Because they're all orbiting the sun in roughly the same direction.
Exactly. If 2 asteroids are in very similar parallel orbits, they aren't slamming into each other head-on at Mach 20. They might slowly drift toward each other at the speed of a slow human walk.
And the gravity of a 30-kilometer rock is tiny, so it doesn't accelerate the incoming object.
Right. The mutual gravitational acceleration is incredibly weak. So when they finally touch, it's not a catastrophic collision. The energy is absorbed by the surface dust, acting like a shock absorber.
It's like a deep space docking procedure between 2 mountains. They just bump and stick.
And over millions of years, minor internal heating and microbombardment slowly weld them together at the neck. We have spectacularly observed this before.
Comet 67P, right, the Rosetta mission. I vividly remember those images. The whole world said it looked exactly like a rubber duck floating in space.
Comet 67P is a textbook contact binary. 2 distinct primordial icy bodies that drifted together and docked.
And there was another one, Arakoth.
Yes, deep in the Kuiper Belt. NASA's New Horizons spacecraft flew past it in 2019. It looked like a flattened reddish snowman.
I remember NASA releasing those 3D red-blue anaglyph images. You could perfectly see the depth of the 2 distinct spherical lobes resting against each other.
Finding Arakoth provided physical proof that this gentle, slow, sticking-together process is a foundational mechanism of planetary construction.
Well, here's where it gets really interesting when we bring this back to Nysa. Nysa isn't a rubber duck. It isn't a 2-lobed snowman. If this interpretation of those 2 deep valleys is correct, Nysa isn't a contact binary at all.
It is a contact trinary.
Which would be the very first one ever recorded in the books. Out of millions of asteroids, the absolute first time we've seen 3 distinct bodies doing this.
It establishes an entirely new kinematic paradigm.
I just want to pause and think about the sheer statistical improbability of that. First, you need 2 massive bodies to drift together at the exact right low velocity to form the initial binary without shattering.
Yes.
Then, a third massive body has to happen upon this fragile pair, match their orbital velocity almost perfectly, and gently dock with them softly enough that it doesn't break the original neck holding the first two together.
The kinematic constraints required for a three-body low-velocity merger are staggeringly tight. It implies a vastly more crowded, dynamically complex environment in the early solar system than we thought.
It's like finding a 75-kilometer-tall cairn of balanced rocks floating in the void.
It really is. It suggests these slow-motion multi-body pileups might have been incredibly common during the primordial era.
But, as with all things in science, a single piece of visual evidence rarely settles a debate immediately. Minker's team left the door open for a completely different explanation.
They were obligated to, because the visual morphology of the asteroid allows for an alternative reading, broadly referred to as the battered rock hypothesis.
Okay, let's explore this alternative. It suggests Nysa is a single, solid body that has just been so deeply battered and indented by impacts that it merely resembles three lobes.
Right. It posits Nysa started as one large monolith, and over billions of years, it was subjected to massive kinetic hits in exactly the right geometric locations to carve out those valleys.
Hold on, I have to push back here. Space is a cosmic shooting gallery. Everything is battered. Our moon is saturated with craters. Why is this alternative theory so special? If I take a baseball bat to a lump of clay, it gets indented. What's unique about Nysa?
To understand why it's just as wild as the trinary hypothesis, we have to talk about the physics of impact cratering versus catastrophic disruption. It is a question of scale and structural integrity.
Okay, explain that.
A standard impact crater is localized. A small rock hits a bigger rock, excavates a bowl-shaped depression, and leaves a scar. We see millions of those, but we are observing continuous valleys wrapping around the entire circumference of Nysa.
Like someone tied a steel cable around a block of cheese and pulled it tight.
Precisely. To create a continuous circumferential feature like that, you aren't getting hit by small meteorites. You are talking about cataclysmic collisions transferring incomprehensible amounts of kinetic energy.
Because Nysa is 75 kilometers across. It's the size of a major metropolitan city.
If it is a solid rock, the sheer amount of impact excavation required to carve those massive valleys without blowing the entire 75-kilometer asteroid into microscopic dust. That survival story would be a scientific first.
Ah, it's the survival aspect. The laws of physics dictate that the energy transfer should have shattered the entire rock.
In planetary mechanics, there's a threshold called the catastrophic disruption threshold. If the shock wave from an impact exceeds the internal tensile strength of the rock, the whole object shatters into a swarm of debris.
So to carve a deep valley without surpassing that threshold,
the Goldilocks nature of those impacts would be statistically astonishing. The impactors would have to be exactly big enough to carve the valley, but not one fraction of a joule more energetic or the whole thing is destroyed.
So either Nysa is an impossibly gentle three-way merger, or it is the ultimate survivor of impossibly precise kinetic hammer blows.
Exactly. Both realities are highly improbable.
So how do we solve a visual puzzle when the image intrinsically supports two completely wild, contradictory interpretations? We stop looking at the rock and we look right next to it.
Which is where the observational paradigm shifted entirely.
Yes, the tiny witness in the glare. I love this part.
While using adaptive optics to study the shape, Minker's team was simultaneously employing a completely different set of imaging techniques. They used high-contrast imaging protocols originally developed for hunting exoplanets around other stars.
That is a brilliant cross-disciplinary hack. Usually you use that to block out a star light years away to see a tiny planet, like standing in New York and trying to spot a firefly around a searchlight in Boston.
That's the exact challenge. The star's glare hides everything. But they took this exoplanet tech and aimed it at our own asteroid belt.
Because Nysa is so bright, it acts like a searchlight itself.
Exactly. Any small object near it would be completely lost in the intense glare of Nysa's reflected light if you use standard techniques. The pixels on the sensor would just saturate.
So they utilized an instrument called a coronagraph. What is that physically?
It is an optomechanical device invented by Bernard Lyot in the 1930s. It places a tiny, opaque physical mask in the focal plane of the telescope, perfectly aligned to cover up the bright central object.
But light is a wave, so it bends around the mask, right?
Right, it diffracts. So a coronagraph also employs secondary masks and complex algorithms to suppress that diffracted light. It creates a localized artificial eclipse inside the telescope itself.
And by creating that artificial eclipse, they suppressed the glare of the 75-kilometer main asteroid, and they found a tiny, faint speck of light. They found a moon.
A distinct satellite orbiting Nysa. And it is absolutely tiny. It is estimated to be only about 1 kilometer across.
A 1-kilometer moon orbiting a 75-kilometer asteroid.
And it orbits at a distance of at least 170 kilometers away from the center of Nysa. It's officially designated S2026-44.
And they had to spot it independently in 2 separate observing runs to confirm it wasn't just a cosmic ray or a glitch, right?
Yes. In astronomy, you can never trust a single observation at the bleeding edge of a telescope's capabilities.
I just marvel at the tech required to see a 1-kilometer rock from hundreds of millions of miles away while blocking out a blinding glare next to it.
What's fascinating here is that while the technological feat is incredible, the actual existence of the moon isn't shocking to planetary scientists anymore. Small asteroids having moons is actually quite common.
That always surprises people. We intuitively think moons are reserved for massive planets like Jupiter or Earth.
It requires a shift in perspective. Gravity scales with mass. Look at the asteroid Dinkinesh. In 2023, NASA's Lucy spacecraft flew past it. Dinkinesh is only 700 meters across, but it had a tiny satellite orbiting it named Selam.
And Selam turned out to be a contact binary itself.
Exactly. 2 smaller lobes stuck together, orbiting a larger rock. The asteroid belt is a highly dynamic gravitational environment.
But finding a 1-kilometer moon near Nysa is more than just cool trivia. It is the ultimate key to solving the mystery of Nysa's 3 lobes.
Yes, because a moon is a continuously running physics experiment. It provides the mathematical key to calculate the fundamental properties of its parent body.
So what does this all mean? How does a 1-kilometer speck of rock tell you what the main asteroid is made of?
It fundamentally revolves around density. And to calculate density, you need volume and mass.
Volume we have securely in hand from the high-res adaptive optics images. We mapped the 3D shape so we can calculate the physical space it occupies.
But mass is vastly more difficult. Visual size does not equal mass. A party balloon and a solid iron cannonball can have the exact same volume but vastly different masses.
You can't just weigh an asteroid on a cosmic scale.
But nature provides a scale for you, provided you have a moon. Thanks to Johannes Kepler and Isaac Newton, we have the tools. The orbit of a moon is dictated entirely by the gravitational pull of the parent object.
And the strength of that pull is dictated by mass.
Exactly. By watching that tiny 1-kilometer moon trace its path, measuring how fast it moves and how far away it is, you can calculate the exact gravitational pull required to keep it in orbit.
You plug those numbers into Kepler's laws, do the algebra, and the precise mass of Nysa drops right out.
Then you divide that mass by the volume from the images, and you get the asteroid's bulk density.
And why does density solve the debate?
Because density physically distinguishes a loose pile of disconnected rubble from a solid, coherent shard of rock.
Let's break that down. If the contact trinary hypothesis is true, if it's 3 separate pieces resting against each other,
the resulting structure is not a solid block. The bulbous lobes don't fit perfectly flush. There are massive empty spaces, huge internal voids at the interfaces where they touch.
like a glass filled with large ice cubes, huge gaps of air between them.
We call that macroporosity. Because a huge percentage of its volume is empty space, its overall mass will be low relative to its size. The calculated bulk density will be very low.
But if the alternative is true, if it's a single battered monolith,
A monolith does not have those massive structural voids. It's solid rock through its core. Its mass relative to its volume will be high. The calculated density will be high.
it's an incredibly elegant scientific resolution. The debate won't be settled by the groundbreaking images that started it, but by the pure math provided by that tiny speck of light.
It's a beautiful synthesis of different branches of astronomy. The imaging gives you the structural question. The classical orbital dynamics gives you the definitive answer.
You now understand how astronomers weigh an asteroid without ever touching it. But zooming out, why does Minker's team care so deeply about the density of one specific asteroid?
If we connect this to the bigger picture, we have to look back at that E-type designation in state-type.
The bright, reflective material.
It only forms under very precise conditions, extremely high temperatures, and a lack of oxygen. When geochemists study N-statite meteorites that have fallen to Earth, they analyze their isotopic ratios.
And what do they find?
The chemical and isotopic makeup of these meteorites is remarkably, almost identically similar to the isotopic composition of the Earth's mantle.
Wait, really? The exact chemical signature of Nysa matches the rock deep beneath our feet.
To a startling degree. This leads scientists to conclude that E-type asteroids are likely the pristine source material from the very inner region of the primordial solar nebula. They formed in the exact same hot, chaotic neighborhood where Earth was actively accreting.
So Nysa is family. It's a direct cousin to the material that built our home planet.
E-types represent either primitive building blocks that never managed to grow into a planet, or they are shattered fragments of the crust of some early planetary body that was destroyed in a cataclysmic collision.
We are looking at a 75-kilometer piece of debris to reverse engineer a process that happened billions of years ago.
Exactly. If the math proves it has a low density, it tells us gentle, low-velocity accretion was a viable force for building larger bodies. If it has a high density, it tells us a story about the extreme violence of planetary-scale collisions.
The sheer scale of time involved is dizzying. We went from a century of blurry frustration to using adaptive optics to reveal a potential three-lobed structure.
And then pivoting to coronagraphs to find a 1-kilometer moon holding the mathematical key to the solar system's origins.
It's a phenomenal detective story. And as we wrap up this journey, I want to leave you with a slightly unsettling thought to mull over. If Nysa is indeed a contact trinary, a gentle amalgamation of primitive building blocks that survived the chaos of the early solar system, consider the solid ground beneath your feet right now.
It changes your perspective.
What if the very foundations of Earth started exactly like Nysa, endless fields of bizarre, lumpy, multi-lobed snowmen drifting silently in the dark, slowly sticking together over eons until they forged a world capable of looking back up at the stars?
It's a powerful image.
Thank you for joining this conversation. Keep looking up and keep questioning the shape of things.